this lesson, we are going to discuss a new topic in rigid body planar kinematics, that is the relative motion analysis using rotating axis. Let's recall the relative motion analysis with translating frame. Let's say we have three objects in this figure. This is one observer. This is a man on a boat at point A, and there is a duck at point B. So the man on the shore, we can set this as our fixed reference frame, and the man on a boat, we can say that this is our translating reference frame, because obviously the man on a boat is moving or is translating during the observation. So we can then, from our previous lesson, we draw a position vector of the man at point A from the fixed reference frame, that is RA or RA/O. And then from the fixed reference frame, we can also draw a position vector of the duck at point B. This is RB or RB/O. And then we can then draw another position vector of the duck with respect to the man on the boat at point A, that is RB/A. This is the analogy of what we have done in our previous lesson. So RA and RB are absolute positions because it is referring to the fixed reference frame, whereas RB/A is the relative position of point B relative to A, because point A is the translating reference frame. So from this vector triangle, we can then derive this equation: RB/A is equal to RB minus RA. Let's look at an example of a moving rigid body. Here we have two rigid bodies, AB and rigid body BC. So to analyze the motion of point B and point C, first we set point A as the fixed reference frame. Then to analyze point B, we can use the fixed reference point, the fixed reference frame at point A to analyze point B. Then to analyze or to calculate the velocity and acceleration of point C, we have to then set point B as the other reference frame, and this is called the translating reference frame. So from here we can then draw the position vector of point B from the fixed reference frame, that is RB or RB/A in this case. And then we can also draw the position vector of point C with respect to the fixed reference frame, RC or RC/A. And then we can draw another position vector of point C with respect to the translating reference frame, RC/B. If you can imagine, throughout the motion of this rigid body, point B is basically rotating about point A. So this should be the motion of our translating reference frame. So the reference frame at point B, or point B itself, is translating in a curvy linear path around point A. So this is why it is called translating reference frame, because throughout the motion it is translating. And this fixed reference frame at point A does not move throughout the motion, and that is why it is called the fixed reference frame. Now if we look at this problem here, we have point D here, point C here, and point A over here. So if we are to set our fixed reference frame at point D, we can calculate the motion of point C. And also, when we want to calculate the motion of point C from point A, we need to set another reference frame at point C. And in this case, throughout the motion, point C does not only translate, but it is also rotate, because point C can slide along this rigid body DE, and therefore throughout the motion, it is going to rotate and also translate. So this is the difference from our previous example. This example involves a rotating reference frame. Let's take a look at another example. In this case, we also have two rigid bodies, AB and also CD. So throughout the motion, point C will rotate about point D and also slide along this rigid body AB. So we can set a fixed reference frame at point A, and to make the calculation easier, for the case of rotating axis, normally we set the rotating reference frame to be coincide with the fixed reference frame. So the red line here is the rotating reference frame, whereas the blue line is the fixed reference frame. And throughout the motion, if you can imagine the motion of point C, this will be the motion of the rotating reference frame. The reference frame is rotating about point A. It is not translating as what we have discussed in our previous lesson, but in this case, the reference frame is rotating about point A. So if we look at this vector triangle again, previously we have derived that RB/A equals to RB minus RA. And therefore, if we differentiate this over time, we will get the velocity VB/A equals to VB minus VA. And if we differentiate it again, we will get the acceleration AB/A equals to AB minus AA. For translating axis, the unit vector ijk do not change with time. So in this case, we have RB/A is equal to xi and yj. In our case, we don't have the k component because this is a planar motion. And for VB/A, it is equal to drB/A over dt. Therefore, we have dx dti plus dy dtj plus dz dtk. In our case, we just have up to j component only. And only x, y, and z are the functions of time. Ijk does not change or do not change with time for translating axis. Now, if this reference frame is now rotating, the angular velocity and angular acceleration of the rotating axis with respect to the fixed axis is denoted by the capital omega and also capital omega dot. Now, we took the same equations that we have derived previously. Now, RB/A is equal to xi plus yj. This is normally what we have when we calculate the position vector of point B with respect to point A. And since the axis is now rotating, not only the x and y component is the function of time, but also I and j component are changing with respect to time. So therefore, I and j are also variables, and to differentiate this is wrong. To differentiate RB/A to get the velocity, we need to use chain rule. Chain rule stated that duv is equal to duv plus u dv. So in this case, drB/A over dt is equal to dx dt I plus x di dt. This is the first component of the chain rule, plus dy dtj plus y dj dt. This is the second component of the chain rule. Now we can rearrange this. We can bring dy dt to the front, so we have dx dti plus dy dtj plus x dy dt, x di dt plus y dj dt. Now this component is the velocity of point B as observed from point A in xy frame. You will see what this means. And the blue part here represents the rotation of the axis. So when the axis rotates, the axis also have its angular velocity, which is denoted by the capital omega. This is to differentiate with the small omega that is used to represent the angular velocity of a rigid body. So since we have d theta over here, we can use the equation from sector in maths, assuming that I and j is equal to 1. So we have di is equal to 1 d theta times j. So di over dt is basically equal to d theta j over dt, where d theta over dt is equal to the capital omega. D theta over dt is the angular velocity of the axis, and therefore di over dt is equal to capital omega cross I, because k cross I is positive j. So this is what we have for di dt. And let's do the same for dj dt. Therefore, for dj dt, it is then equal to d theta over dt times minus I, because dj is now pointing to the left over here. So it is multiplied with minus I. Now this is capital omega, and to get minus capital omega I is capital omega cross j, because capital omega is k cross j is minus I. So we can then substitute di dt equals to omega cross I, dj dt is omega cross j into this equation. Then we have x times capital omega cross I for this part, plus y times capital omega cross j for the second part. Then we can rearrange this equation to have capital omega cross xi plus yj. And from our previous derivation, xi plus yj is equal to rb/a. So the final part of this blue component is then equal to capital omega cross rb/a. Therefore, finally, for the case of rotating axis, to calculate the velocity of point B, Vb is now equal to Va plus capital omega cross rb/a plus Vb/a xy. This represents the red part in this equation. Now let's derive the equation for acceleration. To get the equation for acceleration, we have to differentiate the velocity equation over time. When we differentiate this over time, Vb will get Ab. Differentiate Va, we will get Aa. We differentiate capital omega over time, we will get d omega over dt cross rb/a plus omega cross d rb/a over dt. This is chain rule because these two are variables changing over time. So we need to apply chain rule, and this corresponds to the blue part in here when we differentiate this over time, plus differentiate of VBA xy over time, we will get d VBA xy over dt. So we can then derived from drb slash a, this part here, is indeed equal to our previous derivation. We take this part. So drb slash a is also equal to vb slash a, which is also equal to capital omega cross rb slash a plus vb slash a xy. And dvb slash a dt, this part here, is then capital omega cross vb slash a xy plus ab slash a xy. We can then substitute this expression in this equation here to get this final equation. AB equals to AA plus capital omega dot represent this d omega over dt. It becomes omega dot cross rb slash a. Then we have this part here, capital omega cross. Now drb slash a we take from this. This becomes the green color in this expression, omega cross rb slash a plus vb slash a xy, plus the n here we take from this derivation, this expression, and we have omega cross vb slash a xy plus ab slash a xy. We can still simplify this equation to get this. AB is equal to AA plus omega dot cross rb slash a plus omega cross rb slash a. Now this this omega here, we can then simplify it to get 2 omega cross vb slash a plus ab slash a xy. Okay, we bring this vb slash a to this side here. That's why we get 2 times omega cross this. And we can further simplify to get AB equals to AA plus omega dot cross RB slash A minus omega squared in scalar times RB slash A. This comes from this vector triple products plus 2 omega cross VB slash A xy plus AB slash A xy. So this is the final equation to calculate the acceleration of point B in the case of rotating axis. Let's take a look at an example. There is a horizontal surface in a circular shape where there is a toy duct on the horizontal surface. This circle is currently rotating at omega equal to 0.4 rad per second and angular acceleration alpha of 0.1 rad per second squared. If a toy duct moves along the straight path on the surface with relative velocity and acceleration as shown, determine its absolute velocity and absolute acceleration. So what we want to calculate here is the velocity of the toy duct and also the acceleration of the toy duct. So in this case, we can set point A as our fixed reference frame. The fixed reference frame is denoted by the capital X and capital Y. And then we set the rotating reference frame, which also coincides with the fixed reference frame. The red colored axis is now labeled as small x and small y. This means that the red axis is the rotating axis. So throughout the motion, if you imagine that you are standing on point A, observing the motion of the toy duct as the surface rotates, you can see that the toy duck is moving away from you because the toy duck is traveling in this direction and also at the same time rotating. So this is a very good example of a rotating axis case. In this case, you can see that the toy duck is rotating about point A and also moving away from point A. So to calculate the velocity of the toy duck, we have to use the velocity equation of the rotating axis case. So the absolute velocity of the toy duck is equal to VB. So according to the equation that we have derived previously, VB is equal to VA plus omega cross RB slash A plus VB slash AXY. So let's substitute the value of each of these terms in the equation. So VA, point A is not moving, it is the center of rotation, and therefore VA is equal to 0. The capital omega here is the angular velocity of the rotating axis. It is the angular velocity of the red axis here. And that is the very reason why we define the rotating axis to be coincide with the fixed reference frame, so that this capital omega can take the value of the angular velocity of the surface. So in this case, capital omega is indeed equal to the small letter omega here. So this will take the value of 0.4 K, which is equal to this small omega here. RB slash A is given as 1 meter, pointing to the right in the initial figure. So this will be 1I, okay? And VB slash AXY is the relative velocity of the duck as observed from point A. So this is given by this relative velocity VREL here. So in this case, VREL, the velocity of the duck as observed from point A is 0.2I because it is pointing to the right. So when we calculate everything, we will get VB equals to 0.4 K cross 1I plus 0.2I. And we get 0.4 J plus 0.2 J. We rearrange this. Therefore, we have the velocity of the toy duck VB equals to 0.2I plus 0.4 J meter per second. Now, this first part of the equation represents the absolute velocity of the toy duck or the point B on the XY frame. This is the motion of the duck rotating about point A. Remember that the duck is rotating about point A and also at the same time moving away from point A. So this motion of moving away from point A is represented by the last part of this equation. This is the relative velocity of point B with respect to point A. So this red arrow represents the last part of the equation. This blue arrow going up is the first part of the equation. Now let's see how we can determine the absolute acceleration of the toy duck. Now AB, according to the equation that we have derived earlier, is equal to AA plus capital omega dot cross RB slash A minus omega squared scalar times RB slash A plus 2 times omega cross VB slash AXY plus AB slash AXY. So let's substitute all the values of the variables in the equation. So AA, point A does not move, therefore the acceleration of point A is equal to 0. The angular acceleration of the rotating axis is indeed equal to the angular acceleration of the surface because we set the axis to be coincide with the fixed reference frame. Therefore, this is 0.1k, taking the value of alpha here. RB/A is 1i. The omega here is taking the value of omega in scalar, so 0.4 squared. RB/A is again 1i. 2 times omega is 2 times 0.4k. Cross VB/A is the relative velocity of the duck as observed from point A. So this take the value of 0.2i. And AB/A is the relative acceleration of the toy duck with respect to point A. So this has the value of 0.1i. So when we write this equation together, we get 0 plus 0.1k cross 1i minus 0.4 squared times 1i plus 2 times 0.4k cross 0.2i plus 0.1i. And in the end, we will get AB is equal to minus 0.15i plus 0.26j meter per second square. This is the absolute acceleration of the toy duck. Now let's take a look at the acceleration equation. This part here represents the absolute acceleration of point B on the xy frame. So we have a tangential acceleration of the duck and also the normal acceleration of the duck, which is always pointing to the center of rotation. The last part here is the relative acceleration of point B with respect to point A, because the toy duck is now moving away from point A. So there is another term that is pointing to the right or pointing away from point A. Now, unlike the velocity equation just now, for the acceleration equation of the rotating axis case, we have an extra term here. This green term here represents what is called as the Coriolis acceleration. The Coriolis acceleration is an important mathematical correction factor that must be included when performing calculation using rotating reference frame to correct the absolute acceleration that we are calculating due to this relative motion of the rotating axis. And this, the Coriolis acceleration name was taken after a French engineer, J.C. Coriolis, who was first to determine this mathematical correction factor. So this is the equation to calculate the acceleration of point B in the case of a rotating axis problem.